Okay, this is the next lecture in the series of IIR design examples. The question number 4 is determine the system function HAS for the first order Butterworth filter. This particular question can be rewritten in the form as determine the poles of Butterworth filter, which is low pass filter, for n equals to 1. Sketch the poles of HAS with HA minus S and hence determine the Butterworth low pass filter system function HAS. So this particular problem can be written in two types of question. Then we will start our solution with the given terms. N is given as 1, first order. By seeing n equals to 1, we know given n is odd, and for odd n, poles are given as omega c exponential j k pi by n for k equals to 0, 1, 2 up to 2n minus 1. For putting n is equal to 1, pk will be equal to omega c exponential j k pi, where k will be equal to 0, 1 and 0 and 1 only. Now finding the poles P0 will be equal to omega c exponential 0, that is omega c. P1 will be equal to omega c exponential j pi, which is nothing but equal to minus of 1. Then P1 will be equal to minus of omega c. Now if we will try to plot these poles in the sigma and j omega plane, we can see omega c will lie at the positive side here and minus omega c will lie at the negative side of sigma, that is here. Because they don't have any imaginary component, so there will be no component which will be placed elsewhere, and omega c and minus omega c will lie on the real axis. So we know for a Butterworth filter, poles lie in a circular fashion with the radius of omega c. This circle will be drawn, and for n equals to 1, it has two poles. These poles represent HAS and these poles represent the part of HA minus S. Now to ensure the stability of the filter, only left hand plane poles are to be identified for HAS. Then HAS can be written as omega c to the power n. Then there will be poles. These are left hand plane poles. These things we have already discussed in our regular lectures. So S minus pk. So if you substitute the value, it will be omega c to the power n. N is 1 over S minus P1 only, because P0 is at the right hand plane. So we will not address that particular pole. So it will give omega c over S plus omega c. Now for the normalized system function, we will put omega c is equal to 1 radian per sample. Then HAS will be equal to 1 over S plus 1, and for HAS at omega is equal to 0 and S is equal to j omega, it will be equal to 1. 1 over 1, that will be equal to 1. So that is the normalized function we have obtained, and we have also verified its condition. That's all for this lecture. Thank you.